So this one is called D-RaNGe, and it is a mechanism for commodity DRAM devices to generate true random numbers with low latency and high throughput. And there's a bit of overlap with the previous talk, so I'll just go over those sections fairly quickly. So, executive summary again. Our motivation is that we want a high throughput true random numbers because they enable system security and various randomized algorithms. And many systems, many small systems like IoT devices, mobile devices, embedded systems do not have dedicated true random number generator hardware, but they do have DRAM devices. And so the problem right now is that current DRAM-based TRNGs either do not sample a fundamentally non-deterministic entropy source, are too slow for continuous high throughput operation, or are too slow. And the goal of this work is to provide a novel and effective TRNG that uses existing commodity DRAM devices without modification to provide true random numbers with high throughput, low latency, and no adverse effects on concurrently running applications. So we propose D-RaNGe, which is a mechanism that reduces DRAM access latency below reliable values, and we exploit the DRAM cell's failure probability to generate random values. So in our evaluation, we use even more LPDDR for DRAM devices here, and we find that D-RaNGe can provide a very high bandwidth of random numbers and this is orders of magnitude higher than previous work. We also provide numbers with very low latency. In our evaluation, we looked at how much time it takes to find 64 bits of random values, and we find that we can do that in 100 nanoseconds. And this is also orders of magnitude faster than the previous work. So this is the outline. I'll begin with the motivation. So the high throughput true random numbers are required for many real-world applications, and this is important in cryptography for securely encrypting file systems, network packets, data in standard protocols, and there are many other randomized algorithms, scientific simulation, statistical sampling, recreational entertainment. And true random numbers can only be generated with physical processes that you basically can't predict, such as radioactive decay, thermal noise, shot noise. And these systems that rely on this dedicated TRNG hardware requires these circuitries that actually detects these various physical phenomena. But not all these systems have them. So the smaller devices require, but often lack, a high throughput true random number generator. And if we do enable this on DRAM devices, since DRAM devices are available on most systems, we can enable all those previously mentioned applications on these small devices. So that includes those applications that we mentioned earlier, and there are other use cases such as processing in memory, where we're basically moving compute units inside of memory in order to exploit the internal bandwidth of DRAM rather than be limited by the DRAM CPU bus. And so if we can generate these random numbers in DRAM, we can quickly have these random numbers in DRAM rather than transferring them across the bus. So our goal is to provide a TRNG using DRAM devices that satisfies the characteristics of an effective TRNG. Now let's talk about those characteristics. So first, we want to have low implementation cost. In order to enable them on all these small systems, we don't want to have the system designers implement anything on top of the device. We also want it to be fully non-deterministic, which means that it's impossible to predict the next output given complete information about how the mechanism operates. We also want to provide continuous stream of true random numbers with very high throughput and also with low latency, and also exhibit low system interference as to not significantly slow down concurrently running applications. Also, we would like to generate random numbers with low energy overhead. So again, before going into the key mechanism, we'll talk about the background necessary. Here we talk about the DRAM organization. DRAM bank is hierarchically organized into subarrays, which are just a condensed array of DRAM cells. A DRAM cell is a circle in this diagram, and we have local bit lines that run in columns of DRAM cells, and we have word lines that run horizontally and contains DRAM cells within a single DRAM row. We also have these peripheral units, which are the local row decoder, which chooses which DRAM row to drive, and that basically selects which DRAM row we can read from. Once we drive the data, or once we drive the word line, the data in the DRAM row is transferred to the local row buffer, and that acts as a cache so that we can quickly access access that row if there is any locality. We also have many of these subarrays and grouped, and a single group of these subarrays is organized with a global row decoder, which essentially drives or selects the local row decoder, and there's a global row buffer which amplifies the data out to IO readable values. And we refer to this whole structure as a DRAM bank, and DRAMs are made of many of these DRAM banks. So now let's talk about how we actually access DRAM. Looking at the same diagram, but each of these cells are coalesced into cache lines, as this is the typical granularity that DRAM accesses, that you can access DRAM with. So when you want to access data from a cache line, we must first activate or drive the word line of that row. This transfers the data into the local row buffer, and after TRCD time, we can read that data from the row buffer pretty quickly. Next, in order to read data in the next row, we need to first pre-charge the open row and activate the second row, and this transfers the data, and we can read from that row as well. So here we have the same diagram actually as the previous talk. There's a DRAM cell. We start at half VDD, we activate the row, and it starts to share charge, and after some time we amplify the data to readable values. There's the TRCD, and if we reduce TRCD, we start to induce failures in some of the weaker cells. So now let's talk about the key idea here. So as we saw, a cell's latency failure probability is inherently related to random process variation from manufacturing, and we can extract random values by observing a cell's latency failure probability. So here we have a diagram of where greener are stronger and redder are weaker. And the key idea here is to extract random values by repeatedly sampling DRAM cells that fail truly randomly. And we find that this falls somewhere in between the weak and strong cells. So how do we actually extract random values? We identify all these DRAM cells that fail truly randomly when accessed with a reduced TRCD, and we refer to these as RNG cells. So here, when we have identified an RNG cell, we simply access that RNG cell many times over and over again with a reduced TRCD, and the values that come out will be truly random. And we find that when we reduce TRCD by 45%, we can find a lot of these RNG cells. So how do we actually identify these RNG cells? So we take DRAM and we extract 1 million values from every single RNG cell by accessing them with low TRCD, and refer to these 1 million bits as a bit stream. And we simply pass them through the NIST statistical test suite for randomness. And this test suite looks at bit streams for randomness, and they have many tests, including looking for unbiased outputs of ones and zeros across the entire bit stream, unbiased outputs within smaller segments of the bit stream. So if you cut them up, you should have about equal numbers of ones and zeros. Limited number of uninterrupted sequences of identical bits, so you shouldn't have like 100 ones coming out in a row. We look at the heights in the discrete Fourier transforms of the bit streams, and there's a lot, and you can look at that if you're more interested. So how do we actually maximize the number of random numbers that we're generating with D-RaNGe? So we first, because we can only utilize TRCD immediately after activating a row, we have to alternate accesses to a row in order to induce these TRCD failures. And so we can quickly generate these TRCD failures when we alternate accesses between two rows in a single bank. And that's because if you access a bank, access two rows in a single bank, you're forcing each other row to close before you access the other one. And then you're forced to use the TRCD values. So this maximizes the TRCD failures when using a reduced TRCD, and we'll just show you a quick cartoon of how that happens. So we first activate, and we read with a reduced TRCD, cause some failures, activate the second row, read with a reduced TRC, and cause failures also. So note that we're only accessing a cache line at a time, and so we're actually only able to generate failures within the cache line that we first access of that row. And we studied this on these devices. And so we can just repeatedly access back and forth and consistently generate many of these failures. So accessing cache lines that contain more RNG cells will result in more random values. So how do we do this? So we provide D-RaNGe with exclusive access to the RNG cells so that we're not interfering with random or with concurrently running applications. So in this example, we have an array of cache lines, and we identified two of these cache lines to have many RNG cells within them. So we first allocate these two rows containing those cache lines to the D-RaNGe, and we also allocate the neighboring rows so that we're not disturbing those cache lines with any interference, circuit noise interference, like data pattern dependence, or maybe even row hammer stuff. So we can parallelize these accesses across all the DRAM banks for even higher throughput of random values. So in our example implementation, our memory controller reserves these rows containing the selected RNG cells and the neighboring rows per bank. And whenever a system is not accessing the memory controller runs the D-RaNGe algorithm in order to generate these random numbers. And the memory controller contains some buffer that stores these random numbers so that it can quickly service these requests. And we also expose an API for returning the random values from the buffer whenever requested by the user. So again, in our methodology for looking at real devices, we use the same devices from the previous talk and the same testing chamber. And we also use a cycle level simulator called RAMulator, which we use to look at how D-RaNGe affects concurrently running applications. And we use workloads from the Spec 2006 benchmark. We also use DRAM power, which measures the power consumption of our mechanism, and we use the outputs that we find from RAMulator to collect the power information. So now let's take a look at our results. So how do we know whether D-RaNGe is truly random? Well, we pass it through the NIST test, and they pass with pretty high p-values, so we can claim that they're random, but there's more information in the paper, of course. We next look at the latency for 64 bits of random values, and because the latency is directly related to the density of available RNG cells per cache line, we first show the distribution of the densities of RNG cells per cache line across a bank. So here in our real devices, we find that cache lines can have up to 4 RNG cells. Well, the ones that we studied have up to 4. And most of them have even just 1. So we plot the distribution with a box and whisker plot. If you're not familiar, the medians at the red bar at 50% of the distribution. We have the Q1 and Q3, and the whiskers and outliers, which are further beyond the whiskers. We do this for the three manufacturers A, B, and C, and we find that most of these devices have RNG cells with cache lines with 4 RNG cells in them. So to give you the worst case latency when looking for 64 bits of random numbers, we assume that we're just using a cache line with 1 RNG cell from a single bank. And even with that, we're able to generate 64 bits of random values in 960 nanoseconds. And in the minimum empirical latency, when we have cache lines with 4 RNG cells in them, and we're using every single bank available to us, we can generate them in 100 nanoseconds. So in terms of throughput, we also plot box and whiskers plots here, but because we can only have between 1 and 4, the distribution looks a little weird here. And on the x-axis, we sweep the number of banks, and on the y-axis, we have the TRNG throughput in megabits per second. And this is for a single channel. So for each of these banks, we look at the actual number of cache lines with the most number of RNG cells that we found, and we can simply calculate the throughput using those values, which is number of accesses per second to the single channel multiplied by the number of RNG cells that we have across each of our cache lines. We do this for vendors A, B, and C, and we find that when using 8 banks, we can get at least 40 megabits per second. And in the best cases for the different vendors, we get close to 150 megabits per second, and this is for a single channel. When we use 4 channels, we 4x that, and we find that we can get up to 700 megabits per second. So in terms of system interference, the capacity overhead is fairly low, as we're only reserving 6 DRAM rows per DRAM bank. D-RaNGe is very flexible and can adjust its level of interference by simply getting RNG data from one bank whenever it's not in use and not when the banks are in use. We look at real spec workloads and try to find the pessimistic throughput where we only generate accesses, or we only generate random values when DRAM is idle. And so across the spec benchmarks, we find an average throughput of 83.1 megabits per second. In terms of energy consumption, we use DRAM power and find that we can get a single bit of randomness every 4.4 nanojoules. There are other results in the paper, such as activation failure characterization results. This includes spatial distribution, data pattern dependence, temperature effects, variation over time, and also a detailed analysis on devices of the 3 major DRAM manufacturers, energy consumption, the latency and throughput, and a further discussion on the algorithm for D-RaNGe to effectively generate random numbers, and design considerations for D-RaNGe, overhead analysis, and also further analysis on the NIST statistical test suite. Also a detailed comparison against prior work. So now let's talk about the prior work on DRAM-based TRNGs. So there are quite a few different ways that they do this. The first one we'll talk about is command scheduling. Their randomness source was looking at the time it takes to run a code segment of many DRAM accesses. And since they're saying that when you're accessing DRAM while concurrently running applications are running, it's unpredictable how long it'll take to actually access DRAM n number of times because of memory conflicts, refresh operations, DRAM calibration. And so they count the time it takes to run this code segment and then just use the lower bits of the cycle timer as random values. And they can produce random numbers at 3.4 megabits per second, but we can do it much better. The downsides, again, of this is that their randomness source, well, we claim that their randomness source is not truly random, as it depends on the memory controller implementation and concurrently running applications. And it seems like we might be able to take advantage of that to make it not so random. They also have a much lower true random number throughput than D-RaNGe. The next we'll talk about is cell charge retention, and as you've seen these graphs already, we can go through these quickly, but charge leaks from cells and you can create failures if you don't refresh your DRAM cells. And so when they disable refresh for a refresh interval n, they find that some of these cells fail randomly, and they just look at the data within those cells and aggregate them to create a random bit stream. So again, here's a diagram showing the manufacturing variation across an array of cells, and when we reduce the refresh interval and cause failures, we can take the data out and use those for random data. And their key idea is to extract the random values from just the RNG cells that they identified previously. Unfortunately, again, there's high latency. For them, they showed that they can generate 256 random bits of data per 4 megabyte block of DRAM in 40 seconds, and we're much faster than that. Also, in terms of throughput, they need to either reserve a large area of DRAM to create a high throughput, but even if they reserve a 32 gigabyte DRAM device, they only generate 0.05 megabits per second. We are much faster than that, again. They also have high energy consumption, mainly because they have to wait a long period of time to let the charge leak. And again, we are orders of magnitude faster. The last type of work is startup value based. And when a DRAM device is powered up, some of these DRAM cells have random values due to interactions between all these different circuit elements. So the prior work proposes to power cycle DRAM in order to extract random data within RNG cells in that region. However, there are quite a few downsides, one being we must power cycle the DRAM to generate the random values. This could have very high latency based on power cycle time and data migration if you are using the DRAM device. There's also high storage cost, as you need to either save your data somewhere or just be willing to lose it all. As a summary, compared to all these prior works, we have much higher throughput and much lower latency, and we can continuously produce random values, and we don't need to restart our system. So, in summary, our motivation is that high throughput true random numbers enable system security and these various randomized algorithms. The current DRAM-based TRNGs are not sampling a fundamental non-deterministic entropy source, such as the command scheduling. They're either too slow, and the goal of this work is to provide a TRNG that uses existing commodity DRAM to provide random values with high throughput, low latency, and no adverse effect on concurrently running applications. And so we reduce the access latencies and induce failures in identified RNG cells to repeatedly extract random values. In our evaluation, we characterize these devices, and we find that we have significantly higher throughput and lower latency than previous work. And that concludes the second talk. Any questions?
In the two solutions, in the two papers you presented, do you put more trust in the manufacturer? Do you need to trust the manufacturer for both?
Well, you can always test whether, I guess you can always test for the random number generator whether you're creating true random numbers, but you might be able to spoof like a DRAM device for puffs, but because it's all related to manufacturing variation, that's something that they can't control inherently, right? And so maybe they could provide you with DRAM that doesn't meet your specifications, like it's not at the smallest technology node, and so they might have more control over whether some cells fail or not. But yeah, I'm not sure if it does actually meet specifications. I'm not sure if they could really create a device that returns bad puff responses.
If I measure a lot on the puff,
Yeah.
and then sell this,
Oh, okay, I see.
I can't clone the puff.
Yeah, that's true. Yeah, so in that regard, you might have to trust them. But it does take quite a while to just characterize an entire device, and the manufacturers might be willing to do that, but yeah, I guess that's something to think about. Cool. Okay, I guess we can move on then. Or are we going to take a break? Okay, we can take a break, 10-minute break. Okay, thank you.